Hello, I'm David Noel. Welcome to episode 05 of SMB. The topic today is the structure of the Earth. In recent years, a whole new view of the structure of our planet has emerged. In this episode of SMB, we'll look at the broader picture. Later episodes will give more detail on particular parts of the picture. Let's look briefly at the old and the new picture. You can see from this summary that a lot of the old ideas about the Earth have been thrown out and new ones substituted. Oddly enough, in this new look at the Earth, we start off looking at the stars. In episode 04, we looked at the lives of stars. We saw how, when ordinary fusion stars reach the end of their lives, they throw off their outer shells and leave behind a vortex star. Although all vortex stars are similar, how they have been classified is depending on their mass. Medium and high mass vortex stars have been called neutron stars and black holes. Neutron stars are believed to consist entirely of what can be called compacted neutrons. Neutrons are one of the components of atoms. All the elements heavier than hydrogen have a nucleus containing neutrons. Usually there are at least as many neutrons as there are protons in the nucleus. Free neutrons, that is neutrons not within an atomic core, can exist, but they are not stable. They break down with a half-life of about 8 minutes, turning into a proton, an electron, and a blob of energy. Neutrons within an atomic nucleus are kept from breaking down by the presence of the protons. The protons are able to stabilize the neutrons. In a neutron star, the neutrons are stabilized by the enormous gravity they exist under, so that they don't break down. These neutrons can be called compacted neutrons. Compacted neutrons are sources of enormous energy. This is the energy released if they break down into a proton and an electron. When you think about the process by which a neutron star has been formed, it's obvious that these neutrons must have been present in the core of the star before it blew up. This leads to a general assumption about the formation of stars and other heavy bodies like planets. It's not in dispute that these bodies formed by gravitational aggregation of matter from interstellar space, from what's been called the Ord Soup. The proposition is that when celestial bodies aggregate under gravity from the Ord Soup, when their mass reaches a certain threshold, part of their core is compacted by the gravity. This image shows the conventional division of the Earth into 3 major parts. In the centre is the core. Moving outwards, we reach the mesolayer, a new term for what was once called the outer core, and then the mantle. Above the mantle, we find the crust. This is not continuous over the whole surface of the planet, but varies from about 40 kilometres thick down to nothing. First, we'll look at the core. In older pictures of the Earth, this has been envisaged as a ball of molten iron, as a ball of uranium, and all sorts of other things. In the new model, the core contains compacted neutrons. This proposition follows from the early one, that large bodies aggregating in space have a neutron core. Let's move out one layer. The next layer out from the core in our model is the mesolayer. In the new model, the mesolayer has a completely new role in the life of the Earth. In fact, it can be described as the element kitchen. Within this kitchen, elements are cooked and recooked, simmered and broiled. The process is formally called atomic transmutation. It's well accepted that elements are created and transmuted in stars through fusion of atomic nuclei. Explain how elements heavier than iron exist in the universe has been a struggle for scientists. What they could come up with before now was that they are created in supernovas. When you look at the supernova route critically, the idea that heavy elements form in supernovas just falls apart. The new concept is that heavier elements are formed in the middle layer of large rocky bodies such as planets. How does this work? It's all to do with the compacted neutrons on the outer surface of the core. The neutrons within the core are kept from breaking down by the pressure of the neutrons which surround them. On the surface of the core, however, this pressure is a little one-sided. Neutrons actually at the surface of the core have an increased tendency to break down, to form a proton, an electron, and a blob of energy. This process, although very slow, is what controls both the life behaviour and the elemental composition of the Earth. We'll go on to look briefly at each of these aspects. More detail will be available in other SMB episodes. First, how elements are built up, transmuted and broken down. Here we're observing the interplay of the parts of atomic nuclei, that is, of protons and neutrons, together with energy considerations. With the breakdown of a neutron at the core surface to form a new proton, an electron, and a blob of energy, we're looking at events at the lighter end of the scale. A proton and an electron together form a hydrogen atom. Hydrogen is the initial stage in nuclear fusion, also a good source of energy. The meso layer is actually a kitchen for cooking up elements at every scale. In the laboratory, bombarding elements with neutrons is the standard way of creating heavier elements. In the kitchen, every sort of atomic reaction is taking place simultaneously, building up and breaking down atoms. Eventually, in the outer area of the meso layer, a balance is reached. Now we can go to look at the second item, the energy aspect. We saw that neutron breakdown yielded a proton, an electron, and a blob of energy. It's these tiny blobs of energy which ultimately govern life on Earth. To understand this, we need to look at the Earth's energy balances. Here's a chart of some of the Earth's energy items. The main item in our energy is what we get from the Sun. To give a grasp of the numbers involved, this is set here to 1 million units. Because the Earth runs on an elliptical orbit round the Sun rather than a circular one, there's quite a big variation in solar energy received each day. On January the 3rd, when we're closest to the Sun, we get 70,000 more units than we do on July 4, when we're most distant. Compared to this solar input, the amount of energy used by man is very tiny, only 77 units, and this includes our use of solar energy. On the Earth's surface, heat flows up from the interior. The amount varies with the location, but averages about 213 units per day. In addition, we get a lot of energy generated from earthquakes. This is very variable over times and places, but averages about 7,110 units per day. All the energy we get from within the Earth ultimately originates from neutron breakdown in the meso layer. This includes the biggest item, the energy from earthquakes. The big amount of energy we get from earthquakes is not usually thought about. What's more, if you look in conventional sources for its origin, you'll find absolutely nothing. This is a new idea for the world. There's obviously a lot more to this topic, most of which can be looked at later, but there's one aspect of compacted neutron decay which has huge and previously unsuspected consequences for us. We've seen above that when a compacted neutron breaks down, it yields a proton, an electron, and a blob of energy. The proton and the electron can combine to form a hydrogen atom. The important point is the volume of a hydrogen atom is hugely greater than that of a compacted neutron. The ratio of their volumes, in scientific notation, is about 2.875 times 10 to the 14, or almost 300 million. What this means is that there is a huge increase in the volume of the mesolayer as compacted neutrons turn into hydrogen atoms. This in turn results in very significant expansion in the Earth's total volume. It will be a surprise to many to learn that the Earth has doubled its diameter over the last 200 million years ago, a relatively small part of its 4,800 million year history. That much has been proved by others in arguments lasting through almost 200 years of scientific history. But while the picture has been proved, the origin of the forces involved has not previously been known. In fact, expansion of the Earth is just another consequence of compacted neutron breakdown in the mesolayer. The idea that the Earth could double its diameter over the past 200 million years without any alteration in mass might seem fantastic, but simple calculation, based on the figures given above, show it's very possible. After seeing all the turmoil of the mesolayer, the rest of the Earth's structure seems relatively routine. In the mantle, the layer outside the mesolayer, the composition has settled down. But here, there's much relief of local stresses as the parts move around. This mantle rock can be sampled in places where the crust is very thin. It's called MORB, an acronym for Mid-Ocean Ridge Basalt. MORB is very uniform in composition anywhere on Earth. Above the mantle is the crust, the part on which we all live. The crust has been worked over by erosion, sedimentation, volcanism, mountain building, and expansion processes for over 4 billion years. It is these processes which have generated the caches of metal ores and gem deposits which we exploit today. So that's the new picture of the Earth's structure. Following is a link to a referenced article on the web which gives more detail and links on the. And finally, some links to other sources available to you, both episodes on our YouTube channel and a website including articles which quote established and referenced data. Have a look. So it's goodbye from me, David Dong. I hope you like these efforts to make the universe a bit simpler to understand. Goodbye. Time for another proposition. Million.